So we've been looking at the calculus of polar functions. We've dealt with derivative applications like slope of a tangent line, and we're now going to turn to integral applications. You may remember back in Calc 1 and even the beginning of this semester, we were looking at the integral as a way to find the area under a curve. We'll be doing a similar area application for polar functions. But here's the difference. With a rectangular function, remember how we started? If we wanted the area under some graph f of x between, say, x equals a and x equals b, what we did was we essentially split it into a bunch of little rectangles, right? Those approximating rectangles. And we said the area under the curve was approximately the sum of all those little rectangles. The little rectangles, each one, had a base of delta x and a height of f of x at a particular point, xi. And then when we let the number of rectangles go to infinity, this became that integral. What we'd like to do is see how we could adopt a similar technique to finding the area bounded by a polar curve. Here's what's different. We can't start with just a straight base on the x value, or the x-axis rather, because in polar coordinates, everything starts from the pole. So we're going to have to base our entire area not on rectangles, but rather on the sectors of a circle. So think of it this way. If this is my polar function, r equals f of theta, and I want the area between two values of theta, right? This is theta equals alpha and theta equals beta. What I'll do is I'll take that area, and starting from the pole every time, I'm splitting this into these little pie pieces, or pizza pieces. Each of those little pieces is a sector of a circle. And you may or may not remember, but I'm going to remind you right now from pre-calc, to find the area of a sector of a circle, we take 1/2 the angle of the sector times the radius squared. So let's see what we can do here using that area of a sector formula to approximate this area very much like what we did with the Riemann sums, the rectangles, for rectangular coordinates. We're going to say the area is approximated by the sum of the areas of the sectors. And I'm going to say as k goes from 1 to n. So that would be the sum as k goes from 1 to n. And I'm just going to put my sector formula in here. 1/2 times the angle theta. Well, the angle theta is all of these little angles in here. And since each of those little angles is going to get smaller and smaller as I create more and more sectors, I'm going to go ahead and call that delta theta. So the angles which are shrinking down very small are the delta thetas. And then the r squared, well, let's see, r is f of theta, so that would be f of theta squared. Again, just for emphasis, what we just did was to take our original area of a sector formula, 1/2 theta r squared, and write it for this particular configuration. We have the 1/2. The theta is actually this little delta theta, the tiny little piece of angle. And the r is our curve, r equals f of theta. Okay? So it's that whole sector formula written for each of these little tiny pieces. Great. Well, we know that if that's an area approximation, then I can make that approximation into an exact area if I allow the size of these little angles, the delta thetas, to approach 0. Then we know the delta theta approaches our differential, d theta. So the exact area could be written as the integral of 1/2 f of theta squared times the infinitesimally small d theta. And we're integrating d theta. Our theta values, if you look up at the picture, went from theta equals alpha to theta equals beta. And so there's a formula for finding the area bounded by a polar curve between two specific theta values, alpha and beta. That is stated as a theorem here at the top of the next page. Nothing new. This is just exactly what we just talked about. The only condition here is we do want to have beta minus alpha be between 0 and 2 pi. This won't work if we're going around more than once. So let's use our formula to find the area inside the cardioid, r equals 1 plus sine theta. I've graphed the cardioid for us right here just so we can see it. And our goal is to find the entire area inside this cardioid. So here's our f of theta. So right away, I can say that my area is going to be the integral of, or actually, you might notice here we did pull the 1/2 out of the integral. That's always kind of a nice thing to do, so I'm going to do that as well. Of r squared, or f of theta squared. That in our case is 1 plus sine theta squared d theta. Now all I have to do is figure out the limits of integration. And in this particular case, since I do want to go all the way around, it's probably 0 to 2 pi. But remember, we did sometimes have shapes that got swept out in just 1 pi, so we should probably verify, just to be sure. If I make sure I'm in polar mode, if I graph my cardioid, 1 plus sine theta, that's pretty small. I'm going to zoom in. That's a little bit better. If I start to trace, you'll notice that I'm at 1, 0 here with theta equals 0, and I'm going to trace it all the way around. Until I get back to that point 1, 0 again. There I am. That's 1, basically 0. And notice it did take 2 pi to go all the way around there. So, always worth verifying, because some of them, you remember, were 1 pi, but this one is 2. And so I simply have that integral. I did it on my calculator. That integral came out to 9.425. And when I multiplied the value by 1/2, I got 4.712. And I got a little suspicious. That number looked a little bit familiar. Kind of looked like 3 pi over 2 to me. So I actually backtracked and I said, is that really 3 pi over 2? And in fact it was. The decimals even agreed further out. So I believe the exact value here is 3 pi over 2. If you don't happen to recognize that, it's okay. If you gave the answer as a decimal, I'd be perfectly fine. All right, let's take a couple of other area problems. In example 2, I'd like the area of just one petal of the rose curve, given by r equals 3 cosine 3 theta. Again, I've graphed that for us. Notice with the odd multiplier in here, we only have the 3 petals. We didn't have to double them or anything. Ultimately, my goal is to find the area of just one petal. Any one, it doesn't matter. All right. So once again, I know that I would have 1/2 times the integral of my f of theta squared d theta. And the next thing I need are limits of integration. Now, I can do this the easy, smart way, or I can work really hard for it. And we're going to do it the easy, smart way. I could, if I worked really hard, actually figure out the theta values that give me exactly one petal. But I think it would be a whole lot easier to figure out the total area if we go all the way around and then just divide it by 3. So for right now, I'm going to say this is the area for the whole rose curve. And once again, I want to double check whether this was a 0 to 2 pi or a 0 to 1 pi. So I've got 3 cosine 3 theta. Zoom out just a little bit there. I guess I don't have a choice how far, but there we go. And I want to go ahead and trace this. Actually, it kind of does matter. Let me change my window so I can see it a little bit better. I'm just going to go like -5 to 5 on both axes. It's not a square window, but it's all right. There. If I start my trace, notice that I start out here at 3, 0, when theta is 0. And I'm going to trace till I get back to that point. There we go. We're back at 3, 0. And it looks like I went all the way around this time in just 1 pi. So I'm going to integrate from 0 to pi. When I did that integral, I got 14.14. And so 1/2 times that gave me 7.07. Now again, that's the area of the entire rose curve, all 3 petals. So the area of just 1 petal, all I have to do is divide that by 3. Which gave me, I was keeping a lot more decimal places than this in my calculator along the way, by the way. 2.356 is what I got when I divided my calculator value by 3. So again, much simpler than trying to figure out the specific theta values for just 1 petal. And I would encourage you to use that whole symmetry idea to make your life a little easier in terms of not needing to calculate so many specific thetas. All right. I'm going to ask you to go ahead and skip example 3. It's kind of beyond the scope of what I really expect you to be able to do at this stage of the game, so I'm not going to cover that. I may have written it out in the notes. I don't remember. You can look at it if you want to, but I'm not going to ask you an equation that's quite that complex. Instead, we're going to go over and on page 36, I'd like to look at the area, instead of from the pole all the way out to a function's curve, I'd like to look at the area between 2 polar curves. So I'm going between r equals g of theta and r equals f of theta. Here's the thought process here, and it's very similar to what we did with rectangular coordinates. It's just that I have to use sectors instead of using rectangles. If I think of the sectors kind of like we drew them before, out to that outer edge, we know that the area from the pole all the way to the outer function, so the area to the outer curve, is 1/2 the integral from alpha to beta of f of theta, which is the function out here, squared d theta. But the problem is I've now included a bunch of area that I don't want. So think about another sector in here that only goes as far as the inner curve. If I subtract off that area, I'll be left with the area that I want. It's labeled R in our diagram, so I'll just say R equals. So I'm going to subtract the area to the inner curve. That same area formula is going to be 1/2 integral from alpha to beta. And in the picture, I think I almost drew over it here, but we had called this g of theta, right? This was R equals g of theta. So this time we'll have our g of theta, our inner curve, squared. I can go ahead and do a little combining here and say the area of my region, there's a 1/2 in both of these. Both of them are integrals from alpha to beta. And then I would just have the f squared minus the g squared. So that ultimately is going to be my formula that I'm going to use to calculate the area between two polar curves. Sometimes, like in the diagram that we did before, or actually no, we haven't done one like that yet, the limits of integration, no we did. The limits of integration are sometimes given in the problem, but more commonly we end up having to find them by finding the intersection of the points of a couple of polar graphs. We're going to see an example of that and how we kind of overcome that challenge in this next example. So example 4. I'd like to find the area of the region that lies inside the circle, r equals 3 sine theta. And we can do this on our calculator. Notice that's that circle, radius 3, with its center on the y-axis. So it looks something like this. And then the second one was the cardioid, r equals 1 plus sine theta. So I'm going to add that to my calculator graph as well. And you can see the cardioid, everything's a little bit small here, so let me change my window. I'm going to go, I think, from -3 to 3, and from -1 to 4. They're a little bit easier to see what's going on. So on my cardioid, we've got, let's see, 1, 2 is the maximum value of that up here. And then we kind of come down, go slightly below the x-axis, and come back up. All right, ultimately, the area that we're trying to find is the area that goes inside the circle, but outside the cardioid. So we want this area out here. That's my goal. That's what I want to find the area of. Now, of course, I can see the intersection points, but in order to actually run the integral and integrate from this theta value to that theta value, I'm going to need to know exactly what those are. In my drawing, I can kind of approximate, but we don't know how accurate my drawing is, so we're much better off calculating those mathematically. So here we go. I want the intersection points. Like anything else, to find intersection points, If I have two expressions for r, I just set them equal to one another. So 3 sine theta equals 1 plus sine theta. Subtracting the sine theta, I have 2 sine theta equals 1, and sine theta equals 1/2. Two places where sine theta is a half would be pi sixths and 5 pi sixths. So this intersection point, and I actually drew this one pretty well, does happen to have a theta of 2/12 or 1 pi over 6. And this intersection point, I'm off a little bit more, but not too bad, would be the 5 pi sixths. Again, though, don't go by the drawing. You want to actually solve for them to be sure that you have the right values. All right, we're in pretty good shape. We now are going to write our area formula. And I'm just using the formula from the top of the page. I have 1/2 times the integral. We just calculated the alpha and the beta. Pi over 6 to 5 pi over 6. And then, just as a reminder, in our formula, it was the outer, actually I used pink here, the outer function squared minus the inner function squared. So in this particular case, I always like to imagine kind of what I call it a radial spoke. If I were to start from the pole and just imagine a little sector kind of coming out this way, right? The outer function would be the circle, which was 3 sine theta, right? All the way out here to the circle, 3 sine theta. Square that. And the inner one would be the cardioid, the 1 plus sine theta. And again, not a really pretty integral to do, but thank goodness, calculators help us out a lot. In fact, when I did that integral, I really recognized the decimal. It was 6.28 something. It was just 2 pi. So we end up with half of 2 pi, or simply pi, for our area. All right, so that's great, as long as you've got distinct inner and outer functions. In my last area example, I want to show you a situation where we have area bounded by more than one function, but it's not necessarily an inner-outer situation. Once again, I've got a circle and a cardioid, and I'd like to find the region this time that's in common to the two regions, bounded by the curve r equals -6 cosine theta. That's just going to be a circle, but this time on the x-axis, where it's centered. So that's got to be this circle. And then the cardioid, r equals 2 minus 2 cosine theta. This is the cardioid right here. And this time, I specifically want the area common to both of them. So I'd be looking for the area of this kind of sort of football-shaped region in here that's inside both curves. All right, just like before, pretty clearly we're going to need this intersection points, right? So we might as well get those right away. Those are both expressions for r, so I'll just set them equal to one another. And so let's see, if I add the two cosines over, I'd have negative 4 cosine theta equals 2. Dividing by the negative 4, cosine theta would be negative 1/2. And let's see, that happens right here. And also way down at the bottom here, down here. So at 2 pi over 3, and also at 4 pi over 3. Two pi over 3 would be the second quadrant one. And 4 pi over 3 would be this third quadrant one. All right, next, I need to think about my radial spokes. This is why it's so important to draw these. Imagine, again, a little sector or radial spoke, always starting from the pole and then going outward to the edge of your region. Kind of like drawing a representative rectangle, but in polar coordinates. Well, here, we're going from the pole out to the cardioid, right? For this sector, the circle actually had nothing to do with it. But what happens over here? If I draw my sector a little quicker, right in here, my little sector would go from the pole to the circle. So rather than being between in the terms of subtracting one from the other, what's going to happen here is we're going to have to do more than one integral. For a while, we're going to do the area inside the circle, and then at the intersection point, we'll switch to the area inside the cardioid. And then notice down here at this intersection point, we'd actually have to switch again. Because down here at the end, we're back to having the boundary of our sector be on this circle. I'm going to cheat just a little bit, cheat in a smart way, and say this region that I'm trying to find the area of is definitely symmetric. So I think it would probably be a lot simpler for me if I just split it right here. And if we were to find the area of just the top half, we could double that to get the area of the whole thing. And that way I only have to do 2 integrals rather than having to come back and do a third one. Splitting it in half like that, of course, is splitting it at this theta value, which would be pi. So that's my strategy. Using symmetry, I'll still have to write 2 integrals. So I'm going to have to double. The first piece, the piece that goes out to the edge of the circle, would be 1/2 the integral from 0. Oh, what? Is that 0? It probably isn't, actually. You know what? We better check that. 0 probably goes over here, doesn't it? We better check this on the graph. It was -6 cosine theta, and then 2 minus 2 cos theta. And I probably don't have a big enough window in here. We'll fix that. Looks like if we did like maybe a -8 to 8. That's a bit better. It's not perfectly symmetric, so I don't have a perfectly round circle. I don't need that much over here, though. I want to be able to see a little better. And adapt this one more time. We don't need such positive x values. I'm just going to go to 2. Made it even more elongated, but at least I can see it. All right. So if I start to trace this, and I'm actually going to trace along the cardioid. 2 minus 2 cos theta. notice that as I start to trace, I am going up here along this part of the cardioid, which has nothing to do with my area. So in fact, I don't really even want to start until I get where? I don't really want to start until I get into that second quadrant, right? I don't want any of the area in the first quadrant. I don't want to start till I get the second quadrant, which would be a starting value here of theta equals pi over 2. So this little section is going to go from theta equals pi over 2 to theta equals 2 pi over 3. And for that little section, I'm only going to the edge of the circle. So for the r value, I'll use -6 cosine theta squared. I'm done with that piece. Now I have to add the next piece. Area formula again, 1/2. And this time I'm starting where I left off at 2 pi over 3. And this time I'm going to continue along the edge of that cardioid until I get down here to theta equals pi. I am going to the edge of the cardioid now. So for my r, I'll use 2 minus 2 cosine theta. Whew, that was a lot of work. All right. I did all of this math, and by the way, I just kind of went ahead and distributed to get rid of all those 2's and 1/2s. And when I did those 2 integrals and added them up, I ended up getting 15.71. All right, we're down to our last example. We're leaving area, and our last example is going to be arc length, which is also an application of the integral. All right, formula for the length of a polar arc can be obtained from the arc length formula for a curve described by parametric equations. Here's how we do that. If f as a function has to have a continuous derivative, then the length of the graph r equals f of theta from theta equals alpha to theta equals beta is the square root of f of theta squared plus f prime of theta squared. Or we could also think of that as the square root of r squared plus dr d theta squared. This is pretty much just a formula, not so much setup that we need to do here. So these are, I think, a little easier than the area problems. In example 6, we'd like to find the length of the arc from theta equals 0 to theta equals 2 pi, so all the way around. This cardioid, r equals 2 minus 2 cosine theta. So I'm simply going to use the formula that they gave us. Since we were told 0 to 2 pi or all the way around, I already have that as my limits of integration. And then under the radical, we have r squared. That would be 2 minus 2 cos theta squared plus the derivative, dr d theta. Let's see, that would be derivative of cosine is negative sign, so that ends up being a positive 2 sine theta, also squared. I'll sneak a little d theta over here. Again, although if you really worked hard at it, you could probably figure out how to integrate that by hand. I'm not requiring that you do so. Perfectly fine to use technology to do the integral. And when I integrated that on my calculator, I got 16. All right, that brings us to the end of section 10.3, which is also the end of our discussion of our polar coordinates.